Hello and welcome to your weekly BYOND tutorial. Today we're going to pick up where we left off last week with pixel movement. Last week, we covered some basics of pixel movement, specifically the core concept of it, bounding boxes, and step size. Today, we will expand on how you can get the most out of your pixel movement. Now that we know how to define a bounding box, we need to figure out how it interacts with the world. Being able to move in individual pixels would not be very useful if you could not easily know exactly where the player is in pixel form. Luckily, DreamMaker gives you several tools to let you get the information you want and manipulate it as you wish. These tools are Step X, Step Y, Locks, the Move procedure, the Cross and Crossed procedures, the Uncross and Uncrossed procedures, the Bounds and O-Bounds procedures, and the Bounds Dist procedure. Before we move forward, I need to mention one variable that didn't quite fit into this video very well, and that is FPS. This is a variable that interacts closely with world tick lag, and defines the speed of the world in frames, or server ticks per second. The default value is 10, though when creating a new environment in DreamMaker, the small default code given to you will set the world FPS to 25. The FPS variable is tied to world tick lag in that it is calculated by the formula 10 divided by world tick lag. FPS exists basically as an easier way to look at world tick lag. For example, which one of these values is easier to read and understand at a glance? Both of these settings do the exact same thing, but for most of you, FPS is much easier to understand at a glance. Keep in mind that higher FPS values will hurt your game's performance, and values above 40 or 50 may cause unwanted effects. 40 is a good number to cap yourself at. The client also has its own FPS variable that can be set separate from the world FPS, usually to a higher value. Setting client FPS to a higher value will run the client faster to smooth out animations and glides without affecting the actual server. This can result in a nicer looking game with no additional impact on the server. The client FPS variable is set to 0 by default, which automatically makes it use the same value as world FPS. Lastly on this subject, in case any of you felt uneasy at the idea of modifying the server tick rate because of sleep and spawn, I want to remind you that these procedures run in ticks of real time by default. Sleeping at value of 1 will still sleep for 1/10 of a second no matter what your tick lag or FPS is set to. You can make a sleep run at every server tick by doing sleep world tick lag. For those of you that don't know what sleep and spawn are, don't worry. I will be releasing a video covering things like that at some point. Depending on when you're watching this, it may already be out. Now that we have that out of the way, let's get to that big list of pixel movement features you saw before. Let's tackle Step X and Step Y first. These variables define the position of an atom in pixels relative to the tile it is in. For example, if your Step X is 10, your atom is shown 10 pixels east of the western edge of the tile you're in. The same concept applies for Step Y. A Step Y of 5 means your atom is shown 5 pixels north of the tile's southern edge. But wait, what if I move halfway into another tile? How do Step X and Step Y apply? How do they choose what tile I'm in? This is actually very simple. All atoms have a variable list called locks, which contains all of the turfs that are being covered by that atom's bounding box. The move procedure was also updated for pixel movement with some new goodies. Movements are now separated into two categories, slides and jumps. A movement is a slide if the distance that the atom moves in pixels is less than either step size or full tile size, whichever is largest. Any movement that does not meet the criteria for a slide is a jump. This includes default tile movement, changing Z locations, or even movement into the same turf you are already in without a change to Step X or Step Y. Slides can be stopped part way, while jumps are purely pass-fail tests. Moves' default syntax is as follows. Move's return value will be 1 if the movement is a successful jump, or it will return the number of pixels moved if the movement is a successful slide. A failed movement will return 0. The arguments are fairly self-explanatory. New lock is the new location you are moving to. This can also be the current location you're in if you do not leave it. Dir is the direction of the movement. Step X is the new step X value relative to new lock. Step Y is the new step Y value relative to new lock. The default behavior of move is as follows. First, if the movement is going to make your bounding box leave a turf completely, old lock exit is called for those turfs. If the movement would mean that another movable atom would no longer be overlapping you, that atom's uncross procedure is called. If any of the exit or uncross procedure calls return 0, the movement will fail and you will not move. Second, if the movement would cause you to enter a new turf, that turf's enter procedure will be called. If the movement would cause you to overlap a movable atom, those atoms' cross procedures will be called. If any of these cross procedures return 0, your slide movement can be shortened so that you collide with that atom. If your movement is a jump though, it will fail here. Third, if any of the enter or cross procedures failed in the previous step, the bump procedure will be called for each one. Fourth, if your movement did not fail completely, then your location, step X and step Y will be changed. At this point, old lock exited will be called for any turfs you are no longer in. Uncrossed will be called for any movable atoms you're no longer overlapping. Entered will be called for any turfs you're entering for the first time. And crossed will be called for any movable atoms that you are now overlapping. For example, you can add extra conditions to enter or cross to prevent movement. You can make something appear behind the player by modifying exited or uncrossed, or let the player know where they are by modifying crossed or entered. Finally, we have 3 procedures that help us play with bounding boxes a little more. Bounds, O-bounds, and bounds dist. Bounds and O-bounds are definitely the more complicated of the procedures, as they have a few different ways they can be called. The purpose of bounds and O-bounds is to return a list of all of the atoms inside of a specified bounding box. The difference between them is that, assuming you're using an atoms bounding box as a base to look through, bounds will include the referenced atom in the list it gives you, and O-bounds will not. There are 3 different ways you can call bounds. Let's tackle these one at a time. In this example, the ref argument, set to src by default, is the atom whose bounding box we will be grabbing. The dist argument is the distance we will expand this box in our search. Note that this does not change the ref's actual bounding box at all. We are only using it as a base. A dist of 0 will return only atoms inside of ref's bounding box. A dist of 12 will return all atoms within 12 pixels of ref's bounding box. In this next example, the ref argument remains the same. It is an atom to get a reference bounding box from. The X offset and Y offset arguments shift the bounding box's position relative to ref's bounding box. X offset shifts the search box to the right, or left if you supply a negative value, while Y offset shifts the search box up or down given a negative value. The extra width and extra height arguments are self-explanatory. You can give or take height and width to the search box. In this final example, this format uses absolute coordinates to create a search box from scratch, rather than using a reference atom. In this format, an X value of 1 and a Y value of 1 equates to the lower left corner of the map as a whole. Width and height are self-explanatory for defining the size of the search box. The Z argument specifies which Z level to search on. These different formats provide flexible options for searching around and finding out where things are relative to an atom. With all of that out of the way, let's end on a much simpler note. The final procedure we're going to look at is bounds dist. And it is very simple. It has 2 arguments, ref and target. Supply 2 atoms that have bounding boxes to this procedure, and it will return the distance in pixels between their bounding boxes. And there you have it. We've covered all of the basic core concepts that DreamMaker gives you for pixel movement. Now that you understand all of the tools available to you, you can go forth and experiment. Trial and error are one of the key parts to learning to write code. Don't be afraid to fail. I have once again left the project files seen in this video in the description below. Keep in mind that the file used in this tutorial was made specifically to demonstrate the order that the move procedure works, and it was not set up in a way that will actually work and run. Because of this, the file is unchecked and thus will not be included when compiling the code. If you have any questions or suggestions for future tutorials, feel free to let me know down in the comments. These videos are all for you guys, so I definitely want to make sure I'm making content that you all want. That's it guys, thanks for watching. Remember to leave a like if you are so inclined and subscribe if you want to stay up to date on more tutorial videos. Also remember that I have a Patreon that you can find right about here if you're interested in seeing videos a week early, among other benefits. Every little bit helps me make better tutorials for you guys, so thanks a lot.